Hello guys, how are you? So today we are starting a new topic. Hi Preetesh, hi Sabresh, how are you? Just let me know if I'm audible. If is my voice loud and clear? Just let me know if you're good to start. So today we'll be starting a new topic, work power and energy. All right. So I guess there's no problem with the audio, or I don't know if there is, because I'm not getting response from you guys. Anyway, so why don't I just start by welcoming you to Unacademy JEE English? This is a brand new channel by Unacademy, which is India's largest online learning platform for IIT JEE. And as you know, here everything is taught to you completely in English, so that no student feels left behind. All right. Hi Priyanka, how are you? So the topic that we'll be starting today is work power energy, and this is lecture one of that. And this series is aimed for 2020 aspirants. Oh my God, Hitesh, what are you saying? Are you all right? Oh, that is sad. Wow. Okay, that's good. So stay home, take care, and it's good that you have this platform, where you can stay at home and oh, that's good, that's good, that's good. So take care, yeah? Take care, buddy. And it's good that you have this platform available for you. Hello, Priyanka. How are you doing? So in any case, so as I said, in case you guys don't know, yeah, good luck. I'm sure you'll be fine. Just take care, man. All right. So as I was saying, this series of lectures is aimed to help 2020 aspirants. Okay, so here we discuss the key concepts of topics quick, and the focus is more on problem solving. All right. So before we move ahead, let me just introduce myself one more time. All right. My name is Rohit Dixit. I studied mechanical engineering from IIT Delhi. I have more than 7 years of teaching experience, wherein I have taught at most of the big names in the coaching industry. All right. I myself was JEE rank 447, and I've coached many students to such top ranks. All right. So let's hope I can keep doing that with you guys here. Okay. So moving forward, let me also tell you a bit about the Unacademy subscription and the benefits that this one comes with. All right. So you have live classes. I mean, you have regular batches where you have live classes, so that is going to be great. You get to interact with the educators so they can give you personalized guidance as far as your prep is concerned. Well, I'm great, Priyanka. Thanks for asking. Plus, you have live polls and leaderboards. Then you have test series and analysis. Again, a very important tool required for your self-assessment and improvement. And then you have live doubt clearing sessions, which is a huge plus. All right, for clearing out any of the problems that you might have had while studying or while problem solving. All right, and most of all, on top of everything, you have access to India's best educators with this subscription. So, how do you get this subscription? Follow these easy steps. Install the app, now go to the plus segment, select your goal as IIT JEE and click on get subscription. That's easy. All right. And if you see at the pricing here, the pricing is very modest and reasonable. For 24 months, the pricing comes out to be roughly 1500 a month. So that's just 36,000. I mean, that is very affordable. So Unacademy is trying to provide you a quality education at a very affordable price. So do check this out, guys. And it's definitely worth the cost. Plus, will they teach in English? Yes, Priyanka, why not? I will be launching my courses in English. Of course, that is why I'm here. You already have a lot of Hindi courses running on Plus, right? So I'll be launching English courses on Plus. So don't worry about that. Of course, you're gonna get English courses. So while getting the subscription, you can also use my code RD Live, and using this code, you'll get an additional 10% off. Oh, great! So hope to see you there. So as I said, use my code RD Live to get your subscriptions, and you get additional 10% discount. So already very affordable pricing with an extra 10% off. All right, so definitely worth checking out, guys. Next, do not forget to join us on the Telegram app using the link shown there. All right, in this group, you'll be shared with all the notifications of upcoming lectures and schedules. All right. So now let's get started with the topic of the day, which is work, power, and energy. All right. So first, let's talk about work. What exactly is work? All right. So work, if you notice, for a constantly accelerated motion case, so you have your equation of 2a dot s equals v square minus u square. Hello Pawan, how are you doing? Right. If you look at the equation carefully now, you can multiply both the sides by m. That gives you 2m times a dot s equals m times v square minus u square. So you get 2 times f dot s equals m times v square minus u square. Now what do you realize from here? You will realize from here that the change produced in the velocity depends not only on the force. It doesn't depend only on how big the force is, but on, in fact, a term which is given by s f dot s. So fine, a force was acting. One, for how long did the body get displaced under the action of that force? That also has to count as far as the velocity change is concerned, and also the angle between the force and the displacement count. So we realize that the change in velocity is not only dependent on the force. All right, it depends completely on the term f dot s. That is why we define it separately as a new physical quantity. All right, so because of this relation, we define a new term called work, which is defined as the dot product of f vector and s vector. Its SI unit is Newton meter, which we give a common name of joule. All right. Next, let's learn some things about work. So first, we can clearly see that since it is defined as a dot product of force and displacement, it will be a scalar quantity. Now, obviously, since it's a scalar quantity, and f and s can be at any angle, right? So the angle can be less than 90, in which case, the dot product will come out to be positive. If the angle is 90, then the dot product will come out to be 0. If the angle between force vector and displacement vector is greater than 90, then of course you will have negative work. So work can be positive, negative as well as 0. Now another very interesting thing is that the work done by any force depends on the reference frame. Please remember that. You cannot just say that, okay, the work of this force is this much only. It depends on your reference frame also. So let's take an example. Suppose you're standing in a lift, all right. So if I ask you, what are the forces acting on you? And the lift is stationary. Consider the lift to be stationary. So the forces acting on you would be mg, and then the ground will be pushing you with some n. Now, if an observer is standing on the ground and he sees you to be stationary, right? So if I ask him, what is the work of n being done on you? His answer will be 0, right? S Priyanka is displacement. S vector is displacement. Displacement of the object on which the force was acting. All right. Some things are not very obvious. I will discuss those things in detail again. Just wait for a while. All right. Similarly, if you look at any observer which is, let's say, going up. Suppose this is going up with some constant speed v. Now, how does this observer observe this guy? He will think that the entire lift is going down with v. All right. Now, if you ask him, is n doing any work on this guy? He will say yes, the force is acting upwards and the displacement is happening downwards. So of course there is work happening, and of course the work will be negative here because the angle between the force vector and the displacement vector would be 180. All right. So Priyanka, what class are you in? So remember that your work always depends upon the reference frame. Now, whenever you talk about work, one more important point, you have to specify clearly that work by which force and work on who. All right. So suppose there is a block here, and you have a force F1 acting on it. Then you have another F2 acting on it. Then let's say F3 acting on it. So when you talk about work, you will have to calculate the work of individual forces. All right, you can't say what is the work being done on the object. If you say that, then I need to calculate the individual three works and add them together. So remember, in general, whenever I talk about work, so I have to specify work due to which force. All right. Okay, Priyanka. So this series will not be very helpful for you, as I said in the beginning. This series is meant for 2020 aspirants. So the expectation is that those guys have already studied their class 11th and 12th syllabus once. That is why I'm going over the key concepts quickly, and that is why you may not be able to follow too many things in this lecture. But for class 11th students or 2022 aspirants, I have started a new series wherein I go live on Thursdays, Fridays, and Saturdays. All right. So we have just finished a chapter on vectors and basic maths there. So you can check out those videos, and you can join us from Thursday onwards at 6 o'clock for your class 11 topics. All right. Those will be completely relevant to you, and trust me, they will help you much more than watching this video would, because this video is aimed for 2020 aspirants. So the assumption is that they have already covered all their 11th and 12th topics once. All right, Priyanka, I hope you got that. So as I was saying, whenever we have to talk about work, I will have to specify which force, work done by which force am I talking about. Now, one more important thing, which many of you don't realize, that suppose if I ask you what is the total work done by all the forces acting on the body, right? Then you cannot simply say summation F times dot S. That is wrong. All right, that is wrong. Okay, so remember, guys, this is a very common mistake that people make. All right, that the net work would be summation of F times displacement. Another important point here to be noted is, I think I have made a separate slide for what all misconceptions people have. Yeah, please do that. That'll be very helpful for you. So remember, Thursdays, Fridays, and Saturdays at 6 o'clock. All right. That is when I go live for class 11 students. Okay. So one more thing that people don't realize is that when we are talking about F dot S, so I need to decide which F. So the F for which the work has been asked, and what exactly is S. So one thing which you don't realize is S is not the displacement of the body. It is not supposed to be the displacement of the body. It is supposed to be displacement of the point of application of force. So I'm glad Priyanka had asked what S is. So this is supposed to be displacement of the point of application of force. Alright, a lot of people wrongly think that S is supposed to be the displacement of the object or the body, which is not the case. Please remember, S is supposed to be the displacement of the point of application of force. So at whatever point your F is acting, so let's say in this case when I told you that F1 was acting here, so S would be the displacement of this point, this exact point where this F1 is acting. Alright, not the body. Because suppose what happens if it is moving forward and also rotating, let's say. So it ends up moving somewhere here and it turns like this. So you will say, if somebody asks you what is the displacement, now displacement is something which is defined for point objects, right? You cannot define displacement for a large body. So what you will do is, in this case, if it goes from here and gets here, so you will just notice the displacement of this point, okay? So this is going to be your S vector. So this will be your S vector and not anything else. You will realize in this case that the displacement of different points on the body will be different, alright? So that is why you cannot define a single displacement of the entire body, right? How can you? Because all the different points are getting displaced by some different amounts. All right. So you realize this from here, that all these may be different. So definitely this displacement, which is the displacement of this point of the object, would be different from, let's say, this displacement, which is the displacement of this point, right? And of course, the third displacement would be even different. So every point in a body can have different displacements, right? So in this case, if you realize, the lengths of these might be different because it has not only moved forward, it has also rotated. So it has moved forward, then rotated also a bit. So you will realize different points have undergone different displacements, and displacement cannot be defined for a big body because of that fact. We can only define displacements for points. One point has moved from one position to another. Alright, the entire body is comprised of a lot of points, so you cannot define a single displacement of the entire body. Hi Akash, I'm good. How are you? So because of this, please remember that while finding work and while calculating F dot S, S is always considered to be the displacement of the point of application. Do not forget this. This is very, very, very important, which people don't realize. They make the quick judgment and say that S is supposed to be the displacement of the body. Like always, Akash. Huh? So, now work for a constant force can be defined as W equals F dot S. And when the force is variable, then what do? Then we define it as W equals integral of F dot ds. How do we get to that? Suppose the force acting on a body was variable, right? So let's get rid of this picture. I hope everybody got this concept. What I meant, that why you can't use a word like displacement of the body. Alright. So suppose in another case, an object is moving on a weird path and the force is constantly varying. Alright. So what I can do, however, is that I can break this path into very, very small parts. Alright. So if I talk about a small part and I say that the displacement during this small part of the motion is ds. Now, this ds is considered to be infinitesimally small. So it is that small that I can consider the force to be constant in the duration of this displacement. Alright, so if I think that this displacement is very, very, very small, so I can also assume that during this small displacement, the force would have been constant. Alright, so for this small displacement, the work can be calculated as dw equals F dot ds vector. Alright, because that is how I define the work of a constant force. Right. Now, to calculate the net force or net work, all I need to do is just integrate both the sides. So when I integrate, I get the expression W equals integral of F dot ds. That is how we are getting W as integral of F dot ds. We are just breaking our path into very, very small parts and then adding all the works together. Alright. So you will also note that the work done by a variable force usually depends on the path of the motion. There may be special cases when it will be independent of the path, but usually it depends on the path. So even if the net displacement is the same, this integration might come out to be different. Why? Because what does this integration represent? This integration is eventually representing the area under the graph between f and x, right? And yes, fx and x. Let's say your displacement is happening in some x and the component of f in x direction is fx, because that is what you'll get as your dot product, right? So in that case, the work by variable force is area under this graph, and of course this will depend on the path. So even if your position, initial position and the final position are the same, suppose the body displaced like this or the force varied differently, so obviously the answer comes out to be different. Alright, so remember that. Hello Rohit Sir, how are you? So you need to remember that. That's an important point. Okay then, so if you are feeling revised, so why don't we warm up with a practice problem? So this problem, you've been told an object of mass 7 kg is displaced from a point 3, 2, 7 to 3, minus 3, 6 by a force of 2 I cap minus j cap plus k cap. You have to find the work done by this force on the object. Hurry up, try to solve this. This is an easy one. This is just to warm you guys up. Alright. So let's see a quick answer for this. Alright, so you've been given the initial position, you've been given the final position, you've also been given the force, and you will realize that this force is constant. Alright. Why it is not varying? It does not depend on anything. It is just constant. 2I cap plus j cap minus j cap plus k cap. So how do you find the work due to this force? Simply find your s vector, displacement vector, and do a dot product of f and s. So hurry up guys, give me a quick answer. This should be easy. I hope you guys are trying this problem. This is a very simple problem just to warm you up, just to get you started. Alright, Rohit Sai says 4. Let's see if that is correct. So obviously initial position vector and final position vector have been given. So what will be the displacement vector? Displacement vector would be initial position, final position vector minus initial position vector. So when I do that, I will get 3I cap minus 3I cap, which will be 0. Then I'll have minus 3 j cap minus 2 j cap, so that'll be minus 5 j cap. Alright, similarly I'll have 6 k cap minus 7 k cap, so that'll be minus k cap. So that'll be my displacement vector. How did I get this? I put in the final position. You guys should know that R vector is final position vector minus initial position vector. So what will be the final position vector? S vector can be written as final position vector would be 3I cap minus 3j cap plus 6k cap. Right, that will be the final position vector minus the initial position vector which would be 3I cap minus 2j cap minus 7k cap. So that is how I am getting my S as this. Alright. Now all I need to do is just take a dot product of this with the force. Alright. So I know my F vector. F vector was given to me as 2I cap minus j cap plus k cap. So F dot S. Let's see how much that comes out to be. F dot S would come out to be j minus 5 into minus 1, which is 5, and then minus 1, 4. Yes, the answer is 4 joules, if considering everything is in SI units. Alright. So yes, Rohit Sai, well done. You got the correct answer. Alright. So I hope everybody followed how we solved this. So let's just move on. Okay, so here's another question for you. Now this question says that a small object of mass m can move freely over a vertical quarter circle. So it is restricted to move over this quarter circle only. Alright, the object moves from A to B under the influence of a constant force F as shown. Alright, and the force of gravity. So it is moving from this point A to this point B under the action of this force shown here, which is horizontal, and of course the other force you've been told acting on it is mg. Alright. So if there is no friction, find out the total work done by the force F and the force of gravity. What will be the total work done on the object as it moves from A to B by both F and mg? Alright, find that. So solve this quick. So that's the path. Path is like this. It's a vertical quarter circle. Alright. And the object is moving along this. Alright. And these two forces are acting on it. These are constant forces. Alright. Of course, some third force also must be acting on it. Or maybe N, maybe it's on a bead. So the N is making it move only on along this path. But you have been asked to find the work done on this by the force F and the force mg. So let's find the answer quickly. Alright, this should not be taking that much time. No, Rohit. That is not correct. That is not correct, unfortunately. Nope. You forgot that it has to be dot. F dot S, not F into S. You forgot to take the dot. The force and displacement have an angle with each other. What is the angle? That's your displacement. So of course, since this is D, this will also be D. This will be 45. So right, so this is also 45 and this is also 45. So what is the direction between force and displacement? What is the angle between force and displacement? It is 45 degrees. No, not 90, 45. This is your S vector. Right, this is your S vector. This is the displacement vector. If this is the S vector and the F vector is horizontal, so what is the angle between these two? 45 degrees, not 90. Yes, 45. So F into root 2D into cos of 45, which will be 1 over root 2. So F times D only. Your answer will be F times D. But again, see what had been asked. Find out the total work done by the force F and the gravity. You have to find the total work done by both the forces. So you have to find the total work done by both the forces. So there will be another work which will come from mg. Now mg will act, of course, in this direction and S vector in this direction. The angle between mg and displacement vector will again be 45 degrees. Alright, so what will be the work done by mg? It will also be mgd. So the net work would be fd plus mgd. Okay, I hope you guys followed that. See, there is another way of doing this. So let's see, what is F vector? How can I represent F vector? F vector is minus Fi cap, right? And how can I represent the force of gravity vector? So force of gravity would be minus mg j cap. Alright, how about my S vector? S vector, you will realize it has come down by a distance d and it has gone in the negative direction, x direction by another d, right? So what will be my S vector? I will write my S vector as minus di cap. Why? Because in the x it is going by a distance d in the negative x direction, and minus d j cap. Why? Because it is also going down in the vertical direction by a distance d. So work done by F, how much will that be? That will be F dot S. So that will be simply F times D. Right? Fi cap dot di cap minus dj cap. So you get your answer as F times D. Similarly, what is the work done by gravity? Work done by gravity would be minus mg j cap dot minus di cap minus dj cap. So you get that as mgd. So F due to both, work due to both, work net work would be F plus mg times d. Alright. So you need to remember one thing here, that how are we doing F dot S directly? How are we not bothered about the path? Because F and mg both are constant forces. For constant forces, you can simply use F dot S to calculate your work. Alright, you do not need to bother about the path. For constant forces, remember the work is independent of the path. It is only dependent on the final displacement. So you can directly calculate that from F dot S. Alright. So I hope everybody followed that. So let's move on. Okay, next problem you've been shown. The Fx graph of a force is shown to you. You'd find out the work done by the force to move an object from x equals 2 meters to x equals 6 meters. So take a look at this graph. You have to find the work done by the force in moving the object from x equals 2 to x equals 6. So solve this. So let's see who can give me the answer first. JEE Mains, JEE Advanced cleared in 8 months. That would be a very, very tough ask, to be honest. Very, very tough ask. Alright. See, and in any case, it's a competitive exam, so a lot of problem lies there. I don't know how quick are you with your subjects and how quickly you grasp your subjects and how much time you are devoting daily. It would require a lot of effort. It's a tough task, but I don't know, you can manage it. I think theoretically you can manage it. Why not? But yeah, it's going to be really, really tough. See, the problem is that most of the guys have started doing their JEE prep from class 9 onwards these days. I mean, that's the trend these days. I remember when I took the IIT JEE exam. Yeah, mains you can clear in 8 months. Mains should not be that much of a problem because advanced requires a lot of practice. A lot more practice. Good evening, Trillions. How are you doing? So I remember when I was taking my own JEE exam. Alright. So even at that time, back when I took my JEE exam, people were people used to start preparing for it from class 11th itself. So I think only 2 guys in my entire class were not studying since class 11th. No problem, Rohit. Yeah, so TS Trillions, that should not be a problem. Don't worry, 2 years is good enough. 2 years is good enough. I mean, I only finally prepared for 1 year, right? I took a drop of 1 year. I did not prepare during my class 11th and 12th. And I took a drop of 1 year and I prepared for only 1 year and I managed the 400 rank, right? So it just depends how much hard work you're willing to put, and of course how quick are you to learn your subjects. I was already pretty good at my subjects, even in my school with my school studies. I had a good understanding, decent understanding of the subjects. Oh, I got this amazing teacher, as I said. Initially, I took the exam once while I was in class 11th and 12th only. I prepared on my own. I used to study some books. I would study my course books. Then I would study and solve H.C. Verma. I would even try to solve Erudov maybe at times, but Erudov solving was very, very tough. Alright. Yeah, definitely. That is why I think I can guide you the best. I've been there. I've been through it all. So I remember, so when I prepared for 2 years, 11th and 12th, what I used to do was I was from ICSC board, alright. No, I did not. In the first attempt, I got 4,000 rank. And back then, they used to have only 2,500 seats for IITs. So that was why I missed it in the first attempt. So in the first attempt, what I did was I used to study my course books, alright, and I used to solve H.C. Verma. I was able to solve H.C. Verma, but I tried solving Erudov and I was having a tough time solving Erudov. Some problems, a lot of problems I could solve, but most of the problems I couldn't. Yes, Rohit, that is what made the difference in my entire prep. I realized that, okay, so there I had this friend of mine, alright, who was my classmate, and we used to be on similar level as far as marks were concerned. So he started his coaching classes in class 11th. Okay, so and he went regularly to his coaching classes for 2 years, and he ended up getting 25 All India rank 24 in his first attempt. All right. So when I spoke to him and I asked him, okay, where did I lag behind? So he told me, see, I went to these classes and they have specialized teachers, great mentors who have been teaching for IIT JEE. They will give you specific guidance which you can't on your own. So he suggested that you take a drop. I know you can get a much better rank than this. And he introduced me to all these teachers, and 1 year. So I decided to take a drop of 1 year and I decided to join all these classes. All right. And I was lucky enough to find some very amazing teachers for myself who really guided me very well. And that is how I finally managed to get a rank of 400 from 4000. All right. Okay, let's see. So let's say here is your x equals 2 and here somewhere is your x equals 6. Alright. So let's say this is x equals 6. Okay, so all I need to do is look at the slope of the graph. If this is 60, then what will this be? This will be 30. Right, because this is 0. So I can say since this is the midpoint, so this will also be midpoint. This is a straight line. Alright. Trillions is going to be very tough. Very tough. You need a good coach. You need a good guide. You need a good mentor. Because the problem when you're studying on your own is, though you know the concepts, you don't realize the depth and subtleties of a lot of concepts. And you don't realize a lot of things. I remember when I started going for my classes, and I was obviously studying the same concepts again. I was studying, let's say, Newton's laws one more time, but this time I realized some new things about Newton's laws which I never realized before. So that made a great difference. Yeah, here, I mean, you have to find a good teacher wherever you can. All right. That is what Unacademy is trying to provide you so that you can get good teachers sitting at home. All right. So Unacademy is giving you that option. So here this will be 30. All right. And similarly, if I look at this, so this is a length of 8. So in the length of 8, if the force has dropped down to by 60, so in a length of 2, it will drop down to 1/4 of that, so 15. So this would be 45. Alright, I'm just doing the calculations mentally just to check your answers since the two of you have already calculated. Alright. So now all I need to do is find the areas of these two parallelograms and add them together. So what does the area of a parallelogram have? Half sum of parallel sides into distance between them. So what is the sum of parallel sides for the first parallelogram? It will be half, the area would be half into sum of parallel sides, which is 30 plus 60 into distance between them, distance would be 2, plus the area of this parallelogram, which would be half 45 plus 60 into 2 again. The distance between the two sides is 2. Alright, so this gets cancelled. So this is 90. 90 plus 105. Okay, so 90 plus 105. I'm getting my answer as 195. Okay, let's see if you guys did your calculations correct. How are you getting 120? The answer will not be 120. Oh, sorry. Yeah. Sorry. I said parallelogram, I meant trapezium only. Right. Yes, 195 would be the answer. Yeah, that's what he says. That is really scary. Yes, sorry, Rohit. I meant trapeziums only. I'm using that formula only. Half sum of parallel sides into distance between them is the area of a trapezium. Alright, I just said parallelogram. You're right, they are trapeziums. With the area formula, I said correctly. Alright, the area is half sum of parallel sides into distance between them. So check your calculation, Rohit. It won't be 120, it will be 195. Alright. I think you just found the area of this and doubled it. Even if you double it, then also you won't get that. I don't know. You did something else wrong. I don't know. So check your calculation once because the answer would be this. Alright. Anyways, I hope you guys followed the solution. If you guys followed the solution, then let me know and we can move on. Please let me know. Okay, I'm waiting for your responses, guys. Good. All right, so let's just move ahead. The answer for this is 195 joules. All right. So check your calculations. Okay, so here you have a problem involving a variable force. Okay, you know the force of spring is minus kx, right? Fs is minus kx. So you're supposed to find out if a spring with spring constant 500 Newton per meter is compressed by 10 centimeters from its natural length, what will be the work done on the spring and work done by the spring? So to find both, what will be the work done on the spring and what will be the work done by the spring? Half kx square you must be applying, right? If you apply half kx square, no, the answer is not 50. No, Romy, you can't be, this is a variable force. This is a variable force. You can't just, no, it's not 50. See, the problem is this force, spring force is a variable force. It depends on your x. It's not constant, all right? So what do you do here? So suppose there is a spring here and imagine it has been compressed by x, all right, from its natural length. So let's say you have compressed it by a distance x. So at this point, the force that this spring is applying is kx in this direction. That's what the minus sign signifies, all right? Yes, that is better. That is the correct answer. So that is what the minus sign specifies. It is telling you the direction. Now, the displacement is happening in this direction. So the work would be, integral of kx dx with a minus sign. Why the minus sign? Because the force of the spring, if I'm calculating the force of the spring, it is in this direction and the displacement is in this direction. So that's why I'm getting the minus sign. All right. So when you integrate this, you will get minus half kx square. All right. And x ranging from 0 to whatever final x you have. So that is your answer. Work done by spring. Work done by spring would be minus half kx square. All right. So of course you can substitute your values now and you'll get 1 by 2 into 500 with the minus sign into 0.1 whole square. So that will be 5 by 2 minus 2.5 joules. Similarly, the work done on the spring would be plus 2.5. All right. Why the external force must be getting applied in this direction only. Okay. So fine. Let's solve one more problem. How to find new batch for class 11th in app. Okay. Some courses will be launched. You can go through them. There is no, I don't think anybody launches an entire course for class 11th. A new batch for class 11th. That's not how the Unacademy system works. You have batches in terms of courses, all right. Trillions. So that is how it works there. You don't have too many batches, you have courses mostly. Why? Because every teacher launches their own course so that you can study any course from any teacher. All right, but you can go and check out the app and find all the courses which have been floated by all the teachers. So in case you want to study from me, I'll be floating my courses, I think, in August. Alright, so around 10th of August. Okay, let's see if what he's saying is correct. So a person of 70 kg is going up in a lift with a constant velocity. Okay, find out the work done by the normal reaction. Okay, during the time when the lift goes from 8 meters to 20 meters. Yes, of course, that is correct. From the lift frame, the answer would be 0 because the displacement would be 0. And from the ground frame, the N would be 700 newtons. N would be equal to mg. Why? The person is moving, or the lift is moving with a constant velocity. So it will be, yes, 700. So, and the displacement is 8. So 700 into 8, which is 5600. Alright. So 5600. Yes, Romy, you got both of them correct. Alright. Good. So let's move forward then. Okay. Yeah, so I added this slide intentionally because there are some misconceptions about friction and about work which I wanted to discuss. So as you've already seen, there was this common misconception that students have is that normal reaction never does any work. That is not true. That is only that is true as far as your ground is stationary. All right. If your ground starts moving, all right, normal reaction does work. All right. Even like, let's say there are two blocks which are in contact with each other, and when they are moving, so on the if I'm pushing the block from behind, so who's doing the work on the block in front? It is normal reaction. Okay, I can give challenging problems, but let's wait for a bit for that. Let's wait a bit for that. Okay. So first, let's just quickly go over all the concepts, and then we'll see some tough problems. All right. Okay. So a second common misconception that people have is that static friction can never do work or never does any work, which is again wrong. Firstly, you will realize that, of course, if you change your reference frame, then of course static friction can do work. Similarly, take another example. If I have this phone kept over my hand, and if I'm moving this hand here, so what is the force acting between my hand and the phone? It is the force of static friction. In which direction will it be acting? It will be acting in the direction of motion only. Why? That is the force that is causing the phone to move, right? So in this case, you will realize the static friction is acting in this direction and the motion is happening in this direction. So static friction is doing work. So static friction can do positive and negative and zero works, all kinds of works, all right? Even positive work. A lot of people might think, okay, friction never does any positive work, it always does negative work. So that is not entirely true, all right? So static friction can also do positive and negative works. Kinetic friction, oh, one more thing, if you want to know, that, see, when we're talking about friction, obviously it will have action and reaction pairs. So if you have two blocks in contact, and this guy is applying Fs on this, which is the force of static friction, and this guy is applying Fs on this, which is again the force of static friction. So one thing that you need to remember is that net work done by static friction on the system is always zero. So net work done on a system. All right. The system means including both the masses which are applying the static friction on each other is always zero. So that is something you need to remember. The net work done by static friction force. So suppose in the example when I was telling you, so here of course static friction is acting on the phone and it is doing some positive work, right? Now you must realize that static friction is also acting on my hand. And if Fs is acting on this guy in the forward direction, Fs must be acting on my hand in the backward direction, right? And they're both undergoing the same displacement. So whatever positive work is being done on the phone, same amount of negative work is being done by static friction on my hand. So static friction never does any net work on a system of two masses which are essentially applying this force on each other. Alright, so remember that. That is a very important result that will help you solve a lot of problems. Next, you know that kinetic friction next, a lot of people think that kinetic friction always does negative work, so that is also not true. I mean, in a similar case, even if I just move my hand very fast, wherein my hand was slipping also, even then my phone may start sliding forward. So in that case also, you will realize that kinetic friction is doing a positive work on the phone. All right. However, like as I said, for both the bodies who are applying the force of friction on each other, the net work done by static friction is always zero. Similarly, the net work done by kinetic friction on both the bodies is always negative. Net work on both bodies. So which both bodies? The two bodies which are applying the force of kinetic friction on each other. On both bodies is always negative. So remember that. Okay, also the work done, if the work done on an object is zero, then either the force or the displacement has to be zero. That is also not true. The angle between them could have been 90. So of course that is a case which a lot of times people miss or make quick wrong judgment that okay, one of the force or the displacement must be zero. Similarly, another misconception that happens to people is that, which I haven't added here, the work, the net work by a lot of forces. Like suppose there are 10 different forces acting on a body. So by all forces acting on a body, is equal to summation F dot S. That is wrong. That is a misconception. That is something that people believe which is wrong. Okay. So the net work done by all the forces acting on a body is not summation F dot S. Okay. It may be true. It may be true in some situations. But you can't say that as a general result. Generally, this will not be true. In some special cases, it becomes true. Alright. So remember that. Alright, so let's quickly talk about energy now. So energy, is defined as the ability to do work, and the entire approach of work power energy rests on the relations between work and energy. So what do we know about energy? Energy is a scalar quantity and has the same SI unit as that of work, which is joule. Alright. Now in mechanics, or when we are talking about the energy of an object, alright. So the energy occupied that any object has, any matter has, is usually called mechanical energy, and it is divided into two components: kinetic energy and potential energy. There might be other forms of energy which are just let's say light energy, heat energy, but I'm talking about the energy that matter can acquire. So if I'm talking about a mass, what kind of energy it is acquiring? In mechanics, we just talk about two kinds of energies, kinetic and potential, and we break them and combine, they are called mechanical energy. So let's talk about the kinetic energy first. So what is kinetic energy? It is the energy possessed by a body by the virtue of its motion. You guys know that, you've studied that definition in class 9. Now, how do I define this mathematically? So mathematically, if you have any object which is moving with a velocity v, then you can define its kinetic energy as the amount of work required to get this body from zero velocity to some v velocity. So imagine if a block of mass m was initially stationary and is finally moving with v. So all you need to do is, what is the work which is required to get this from this state to this state? That will be the work, that will be the kinetic energy. And let's see how that comes. So as you can see, since you know that work is integral of f dot ds, now f can be written as ma, so I can write this as m integral of a dot ds, and a dot ds becomes v dv. Okay, so I hope you guys already know that. I'm not going to show you how a dot ds comes out to be v dv. Alright, I'm not going to show you right now, but you need to know this relation. The dot product of a vector and ds vector will come out to be v dv, where v is mod. Okay, so the vector signs are gone, obviously, because the result had to be scalar. So it comes out to this. So when you integrate both the sides, when you integrate this, what do you get your work as? You get your work as half of m times v square minus 0 square. So that is what kinetic energy is. So what happens is, if a body is at rest and then it starts moving with the velocity v. So this is the work that I must have done, or somebody must have done, on the object to get it to that velocity. So in return, what will happen is, if this body ever comes to rest again, so whatever work I already did on it to get it to move with velocity v, it can again do this same amount of work on another object. It can transfer this energy to another object. Alright, so that is the amount of work it can do on another object or whatever object tries to stop it. Suppose I put my hand here and I'm trying to stop this. So fine, moving here and here, it comes to stop. So how much work will this object do on my hand? It will do the exact negative work. If I had to do half mv square of work to get it from 0 to v, then while going from v to 0, it will end up doing the same amount of work on the object which is trying to stop it. So that is why you call this kinetic energy. How did we define energy? Energy was the ability to do work. So any object moving with a speed v before coming to rest can do a work of half mv square on an object. Alright. Yes, Sabridge, go ahead. Tell me. No problem. Please go ahead and ask. Yes, absolutely. Go ahead. Just make it quick. Yes, Thor, I'm waiting for your question. What is scope of mathematical and computing branch? Oh, it's great. It's great. It's great. I mean, I did not know at the time I was joining IIT. When I was joining IIT, I mean, this branch wasn't too popular. I think it had started only a few years before I joined IIT. I think it had started only, I think, five years ago before I joined. So it was still a very new branch at that time. But afterwards, it gained a lot of popularity because, a lot of recruiters that are coming, I mean, are from banks, iBanks, and consultings, and a lot of data analytics is required, in those kind of job profiles. And this job, this particular degree prepares you for that. It is mathematics and computing, so maths, a lot of maths is being used in these jobs these days, especially with everything becoming automated and you have enormous data sets, so a lot of data analysis is happening, big data analytics is going on. So yeah, that is where this branch became very very popular because a lot of recruiters show a lot of interest in this. So this is a wonderful branch, I think, and that is why I think the ranks have gone up and the cutoff rank for this has gone up. I mean, at my time, I think you used to get this branch for even 1600 rank. Yeah, I think it was so it would still be the same, but the top ranks have gone up. The top ranks opting for this branch have gone up. That time, I don't think anybody with a rank under 500 was opting for this. So yeah. Hello Aditya. Okay. All right. Good to know. Yeah, it has certainly become very, very popular among students over the years. I know. I know, Thor. I realized that even when I was in IIT, I remember when I was in IIT, a junior of mine had come to me and school junior. He was my school junior. I was home for holidays, NChem holidays, and this guy asked me. He had a 1200 rank and he wanted to know which branch he should opt for. And I suggested mathematics and computing, and he was very very happy. Okay, Aditya, good to know. So that is how you get the expression of k equals half mv square. Why is it coming half mv square? Because this is the amount of work which will be required in making an object at rest move with a speed v. And we can inversely say that whenever this object moving at v comes to rest at speed 0, it will end up doing the same amount of work on any object. So since energy was ability to do work, so any object moving with velocity v or speed v can do this much of work before coming to stop. That is why we call this kinetic energy. This energy is present in it if it is moving. If it comes to stop finally, then this is the amount of work it will be able to deliver on some other body. Alright. So let's talk a bit more about kinetic energy. First thing, of course, it's a scalar quantity. Second thing, of course, it can only be positive because half mv square. All right, so half mv square. V square can never be negative. M can never be negative. So this is always positive. Again, it also depends upon your reference frame. Alright. Suppose if an object is at rest and being observed by two observers, one object at rest and another object is moving with a speed v himself. So this guy will not see any kinetic energy in the block, and this guy will see that the block has a kinetic energy. So this is also a frame dependent quantity. It depends on your frame of reference. Remember that. Again, it's an instantaneous quantity. So we can talk about average kinetic energy, but usually we don't. Usually we are always talking about the instantaneous value of this. Alright. Next, the expression K equals half mv square is actually only defined for a single point mass. Please remember this. It is only defined for a single point mass. Half mv square is only defined for a single point mass. Okay. Yeah, you use that for bigger objects also, but you can't directly use it actually. You use it using the CM concept. Alright, we'll talk about that more when we are studying CM, center of mass. So in any case, for now I can just simply tell you that if suppose a big block is moving with the speed v. Now I know that big block is comprised of a lot of small point masses. Right? And what is the property of the block? That block is a rigid body. So if it is a rigid body, all the point masses inside it are moving with the same speed v. So I can write, so as you can see, that for a big body made up of many point objects, the K is written as the sum of K of all the point masses that constitute that body. So if here, let's say this is made up of a lot of point masses let's say M1, M2 and so on. And the total mass M is nothing but, total mass is M, which can be written as summation of all the individual masses. Alright. So how can I write the K of this body? The K of this body would be sum of the K of all the objects, which will be half m1 v square plus half m2 v square and so on. Why every mass is moving with v? Because this block is a rigid body. So as long as you're talking about a rigid body, then you can write the K of the entire block as m times v square. Why? You take half and v is common. What are you left in the bracket with is m1 plus m2 plus m3 till m infinite, whatever number of masses you have, and that is m, which is the total mass of the object. So remember, if the object is not a rigid body and if it's not translating, so this is a very, very special case where you can write the kinetic energy of a big block as half mv square. There are two conditions. One, the block has to be a rigid body. Second, it has to be in pure translation. Alright, so if it is only translating, if it started rotating also, now you will realize that when this is rotating, different points are moving at different speeds. So here, the top point is moving with a different speed, the bottom point is moving with a different speed, and the center is moving with a different speed. So here, all the objects are moving at different speeds. So for such a body, which is along with translation also rotating, I cannot use the expression half mv square. We'll talk about that when we come to rotation. But remember, this half mv square expression is valid only for a single point mass, firstly. Second, if you have a bigger object, you can imagine it to be made up of individually very, very small point masses, and as long as that object is one, rigid, two, translating, or in the state of pure translation, then you can write the kinetic energy as half mv square. So that's a very, very, very special case. Do not generalize it. You cannot write the kinetic energy of any big object of mass m as half mv square. Why? Because you may not be able to define a single v also. Why? If all the points of that object start moving with different speeds, what happens? There is no single speed that you can define. Alright. One more thing. You can also, K is actually also defined as half mv dot v. You know that v dot v is nothing but mod v whole square. So if you wanted to write it in vector form, you could have also written as half mv dot v. Okay. Alright, let's practice some problems now. So a block of mass 5 kg is moving with a speed of 4 meter per second. Find the kinetic energy of the block in the ground frame and in the reference frame, wherein an observer is moving with a speed of 2 meter per second in the direction opposite to that of the block. So find the kinetic energy of such a block into reference frame 1 ground and from the reference frame of a moving observer. So do this quickly. This should be very, very easy. Just quickly do this. This is very easy. And remember all the important points that I'm talking about. Those small little points. They're very important. 10 and 30. 10 and 30. No. Why 10? It's half mv square, Pavan. It's half mv square. Half into 5 into v square, which would be 16. So 5 into 8, it will be 40, Pavan. Hello, Dr. Rash. Yes, Pavan. I'm surprised you're making that mistake. You usually get your answers very right. So remember, even if it's a big block, how am I writing the kinetic energy as mv square? Because the entire block has been told to you to be moving with one speed. So as long as all the point masses are moving with one speed, then you can write your kinetic energy as half mv square. In any other case, you can't directly just write it as half mv square. You will remember your cases of rolling. Yes, 40 and 90, those are the correct answers. Yes. So from the ground frame, the answer would be half of 5 into 4 into 4. So that will be 40. And from the reference frame of the observer moving in the opposite direction with 2, he will see that this block has a speed of 4 plus 2, which is 6. So this will be my W1 and W2 from the moving observer's reference frame. The answer would be half into 5 into 6 into 6. So that will be 30 into 3, that is 90. Let's add the units, joules. No problem, Pawan. But be careful. It's okay. You take your time, but give the correct answer. All right. So let's talk about the work energy theorem now. Now this is the important part. This is how you solve the problems. Okay. So let's talk about this. You will realize that the net work done on any object can be related to the change in its kinetic energy as follows. How? Let's see. We know that summation of all forces, summation F, can be written as ma. You also know that m times A dot ds will be m times v dv. I told you that earlier, that A dot ds becomes v dv. I'm not showing you how because we don't have enough time. For class 11, guys, I will definitely show how this happens. Okay. So instead of A dot ds, I'm writing v dv. So when you integrate f dot ds, what do you get? You get into m times integral of v dv going from u to v. So you will realize integral f dot ds will be equal to half mv square minus half mu square. So this is nothing but the total work. Alright. So here I'm assuming that all the objects are translating right now. This is under translation. That is why I'm writing it net f integral also. I can write it as net f integral also, because every point will have the same displacement. So you will notice that the net work done by all the forces acting on a body is equal to the change in its kinetic energy, and this relation is called work energy theorem. So what does work energy theorem say? Work energy theorem says that the net work done by all the forces acting on a body is equal to the change in its kinetic energy. Remember this. Okay. So let's see. This is how you will solve your problems. All right, using this. So this is the equation of this topic. All right. So let's try a problem with the help of this. An object is dropped from the height of 10 meters. Find out the velocity or speed rather just before hitting the ground using work energy theorem. All right, let's do this quickly. Yeah, there is slight issue. I know. There is slight issue with the connectivity. But it's not lagging that much, don't worry. It's not lagging that much. So it'll be fine, don't worry. So let's see, how do you calculate this? This is easy to calculate. Come on, guys. So what have you been told? You've been told some mass m drops by a height of 10 meters, and you have to find its velocity just before hitting the ground. So u, you know, is 0, v is what you are interested in, and you know that this height is 10. So how do you do this? You know, when you have dropped something, what is the force acting on it? So during the entire duration, the force acting on it is mg. Now mg is a constant force. Alright, so force acting on the block can be written as minus mg j cap. I am taking this as my y and this as my x. Okay, so if I use these sign conventions, then I can write my force of gravity as, the mass is not important, Pavan. The mass will cancel out. It's not important. So similarly, what can you write your displacement as? Displacement can be written as minus 10 j cap. So what will be the work? Work would be F dot S. Why? Because it's a constant force. I don't need to do integral F dot S. So work will come out to be minus mg into minus 10. So that's plus 10 times mg. That's the work. And I know this should be equal to, from work energy theorem, I know, from work energy theorem. What can I say from the work energy theorem? I can say that this work 10 mg must be equal to half m times v square minus u square. U square was 0. So you realize the m's will get cancelled and v would be root 20g. Alright, so if g is 10, then that will be 10 root 2 meter per second. Alright, so the mass does not matter. Pavan, hope you can see that. Of course, you also knew this result when we studied kinematics. If a mass drops by height h, its speed at the end is root 2 gh, which is what we are getting. But this time we are just doing it using the work energy theorem. Hello Kushal, how are you? So let's try another problem. An object of 5 kg mass falls from rest through a vertical distance of 20 meters and hits the ground with a velocity of 15 meter per second. Find out the work done by drag forces on the object. Alright, so here the point is that this is another application of work energy theorem. So, you know, in practical life, whenever a block is dropping down, mg is not the only force acting on it, right? So, of course, there is mg. Then there might be drag forces. What is a drag force? Drag forces mean resistive forces, like air resistance. So, air resistance and all are counted as drag forces. So, F drag, let's call it Fd. So, there are two forces acting on it, mg and the drag force. Now, usually the drag force is not constant, but here it doesn't matter. In any case, you've been asked to find the work done by the drag force. So, drag force is variable. It usually depends on the speed. Alright. So, the faster you move, the faster air resistance the greater the air resistance you feel. So, of course, since you don't know anything about the drag force, how it is varying with distance, so it won't be very easy to calculate the work by drag force. However, that can be done very easily with the use of work energy theorem. Okay. So let's see how. So you were told that this block was initially at rest. It drops by a distance of, and v has been told to you as 15 meter per second. And you've been told that the height it dropped was 20. Alright. And the two forces acting on it are the force of gravity and the drag force. Alright. So let's say what will be the total work done? So total work done by all the forces acting on the body would be work done by gravity plus work done by drag forces. Alright. So what will be the work done by gravity? The gravity forces acting downwards is equal to mg. The displacement is also downwards, which is equal to 20. So the work done by the force of gravity can be written as 20 times mg plus work done by drag force. This will be equal to, from delta ke, okay, from work energy theorem. From the work energy theorem, I can say that this entire term will be delta KE, and that is how I can easily calculate the work done by drag forces. The work done by drag forces would be half. What is the delta KE? What is the change in kinetic energy? It is half m v square. V I know as 15. So 15 square minus 20 times mg. Alright, so let's see how much that comes out to be. So that will come out to be, take your m common. If you take your m common, you have 15 square, which is 225, I think. Yeah, I think. Over this to minus 200. Alright, and m was given to you as 5 kgs, if I'm right. Yeah. M was given to you as 5 kgs. So since M was given to you as 5 kgs, so you write this as 5 times 225 minus 400 over 2. You will realize that the force coming out is negative, which is generally the case with drag forces or resistive forces. Alright. So you realize your answer is 5 times minus 5 times 175 over 2. Okay. I hope everybody followed this. Let me know if you have any problem regarding this. Alright, you guys clear about this? Okay, why don't we discuss a couple of more conceptual questions if you're clear with this. I had this very nice question that I wanted to ask you guys. So I'm getting rid of this, okay? Or maybe let's find a blank sheet. I think I have left a blank sheet somewhere. Yeah, right here. Okay, so here's my question. Question is, but yeah, you'll need to know the momentum conservation for this. Then since you guys are 2020 aspirants, I assume you know the conservation of momentum. Alright, so a man of mass m is standing on a plank of mass capital M. Alright. So let me just quickly write the question. A man of mass small m stands on a plank of mass capital M. Alright, initially both of them are at rest. That has been told to you. Initially both are at rest. Okay. Now, you've also been told the ground is smooth. So there is no friction between the ground and the plank. So the ground is smooth, but there is friction. There is friction between the man and the plank. Now you've been asked if, alright, let's just relate these two masses. Let's not give two different masses. Let's just write this as, let's say 5m, or let's just give it some number. Instead of writing it capital M, you just call it 4m. Alright. So capital M equals 4m. Alright, so where was I? So the question goes like this. A man of mass small m stands on a plank of mass 4m. Initially both are at rest. The ground is smooth, but there is friction between the man and the plank. Now if the man starts moving on the plank with a speed of v with respect to ground. Alright, so man finally started moving on the plank with a speed v. Now how will the man move? Who will be doing the work on man? Who is doing the work on the man? Think about this. Think about this. If the man starts moving, initially man was at rest. So what was his kinetic energy? His kinetic energy was 0. Finally, if he's moving with half mv square with v, then his kinetic energy is half mv square. So his kinetic energy changed, which means somebody did work on him. Who did this work? Yes, friction. Very nice. So what is the work done? What is the work done on the man by the force of friction? Find the work done by friction on man. Now let me make one thing very clear. The answer is not half mv square. Just in case you're wondering, okay, why is he giving us such an easy question? Isn't it very easy? Isn't the work directly half mv square? No, that is not true. The work is not half mv square. In fact, I will discuss the situation. This situation is unique and interesting. Alright, very interesting situation. So think about this. A man of mass small m stands on a plank of mass 4m. Initially both are at rest. The ground is smooth, but there is friction between man and the plank. So if the man now starts moving on the plank with the speed v with respect to the ground, you'd find the work done by the friction on the man. So, Pawan, you were right in saying that friction will do work on man. But friction is not the only one doing work on man. There is one more component or one more kind of force which is doing work for man. It is his internal force, muscle force. That is why you feel tired when you're walking too much. So muscle force is also working on the man. So there are two forces working on the man, friction and muscle force. Alright, not friction alone. Half mv square, as you know, is the work done, net work done by all the forces. So half mv square is actually the sum of work done on the man by friction plus the work done on the man by his muscle force. Alright. So if the man moves forward, the plank will move backward. How can motion be possible? Why not? Why not? Pawan, have you tried ever walking on those travelators that they have on airports? On the airports, you realize they have these travelators where these are constantly moving and you can still walk on those, right? Just like an escalator, there's a travelator which keeps on moving in the horizontal direction, right? So have you never moved on that also? Either you can keep standing on it and it will take you from one place to another. But if you are in a hurry, you can move on your own also. So where this is moving, you can also move on top of this. Or you can move backward also. I'm assuming the plank is long enough. Plank is pretty long, don't worry about it. Okay. Alright, let's just discuss this quickly. Because this is a very tricky kind of a question, alright. You might not be able to figure this out on your own. So why don't I discuss this? So initially both these guys are at rest. You will also realize that there is no external force acting on this, right? So the total momentum of both man and plank will remain the same, even if friction acts between them. Friction is acting between them here, but the friction is an internal force. Since there is no external force in the x direction, the x momentum will remain conserved. So what is the x momentum initially? So I know P initial x is 0. So and also finally I know that the man is moving. As seen from ground, the man is moving with a speed v. So let's assume at that situation the plank starts moving here with some v dash. So what will be the final momentum now? The final momentum now, P final in x would be mv minus 4mv dash, right? Because the mass of the plank was 4m. So from here, I know both these will be equal. So therefore, what I get my v dash as? V dash is v by 4. Alright. Now, why did we do that? We did that because it's very tough to calculate the work on by friction on the man, because man has two things doing work for him. One, the friction, and other, the muscle force. However, what about the plank? What about the plank? Who is doing work on the plank? Only one force, the friction. That is the only force acting on the plank, right? There is no other force. The plank doesn't have any muscles or internal energy that it can spend to achieve this kinetic energy that it got. So the only way it got this kinetic energy was because of the work done by static friction on it. So now I know what is the work done of static friction on plank. Work done of friction on plank. That will be half times 4m into v by 4 whole square. Alright, half mv square. So let's see how much this comes out to be. This will come out to be 1 over 8 mv square. Alright. Now you will need to remember one small little thing. Now, is this positive or negative? Is this going to be positive or negative? This is going to be positive, by the way. This is positive. Why? The Planck initially had zero kinetic energy. Planck finally had a positive energy. So friction, static friction, did plus 1 by 8 mv square amount of work on the Planck. Now, if you remember, I told you that the net work done by static friction on both the objects that it is acting on is always zero. Alright? Which means that the friction did a negative of this work. So work done by friction on man will be minus half 1 over 8 mv square. So now you realize you can also calculate the work done by man's muscles. So let's see. Work done by muscle force on man. He gained a total kinetic energy of half mv square. Right, and you need to add this also because this much negative work was done by friction. So you realize your answer comes out to be 5 by 8 mv square. So that is the work that his muscles are doing. Had he been at rest, okay, that's a very tricky situation. So let me try to show that to you with the help of a diagram what I meant. So imagine this is the Planck, and let's say this is the man. Now imagine when he's moving this foot forward. When you're walking, what is happening? Let's see. So when you are walking, okay, forget about the Planck. Let's talk about you walking on the ground. When you're walking on the ground, what is the work done by friction? Hello for education, how are you? When you're walking on the ground, what is the work done by friction? How much work is friction doing on you? Assuming there is no slipping, you're not slipping on the ground while walking. The work done by friction in that case is zero. If you have you ever noticed, you push the ground. No, no, Pawan, that is not correct. Not half mv square. I mean, imagine you standing here. Now you push the ground. You put your other foot forward and you lifted this, right? Then you push the ground. You put your other foot forward and you lifted this. So wherever the friction is acting, how is the work defined? No, for education, I will not have much idea about that. It will be best if you ask a maths teacher. So if you realize what was the definition of work? Definition of work was F dot S, where S is the displacement of the point of application of force. Now where is friction acting? It's acting between this foot and this ground. However, this doesn't move. Why? Because I lift my leg, right? So the work done by friction when I'm walking is zero. You realize this, Pawan? When you are walking, then the work done by friction is zero. The half mv square kinetic energy that you are gaining, all of it is coming from your muscles. Your muscles are working. That is why you start feeling tired after walking around a lot. Did you get that? Yes, Chamka, very good. Now, if you've ever traveled on an let's say travelator, as I was saying. So this is moving forward, you're not moving. Now you see the friction is doing work, right? Now half mv square is being done by the friction when you're moving on a travelator. Why? There is friction acting here between the foot and the ground itself is moving, right? So now static friction is acting, is doing positive work on you. Now in the case of a travelator, when the ground itself was moving forward and you're not doing anything, then you can say that the entire half mv square is being done by friction. And that is why you will realize if you're standing on a travelator, you can keep standing there for half an hour, 1 hour. You don't start getting tired due to the traveling motion, right? Maybe from standing, yes. But you will not get tired from moving forward. Why? Because your muscles are not doing any work. Alright. So yeah, it's a tricky concept. It's a tricky concept. That's why I wanted to discuss this. So while moving on a travelator, you don't feel tired because there your muscles are not doing work. There friction is doing all the work. But when you're traveling normally, then it is your muscles that are doing work and friction does not do any work. Now in this case, even when these two are moving, this guy forward and this guy backward, alright, what is happening is that imagine when he lifts his foot. So suppose this is also moving and this is also moving. So I am standing like this. Now I push this move backward and I press my next foot here and then I push this move back further and this is what is happening. So consider this motion. When I have lifted my foot from here and I have pushed this back. Now of course friction has done work, right? The friction on the plank was acting backward, right? And this point where the friction is acting has moved backward. Right, so on the plank it is doing positive work. What about the work it is doing on me, on the man? It is doing negative work on the man. Why? On the man the friction is acting in the forward direction. And the plank or the point where the friction is acting is moving backwards. So friction is acting in this direction, but the displacement of this point is backward in the opposite direction. So you will realize on the man friction will be doing negative work. Alright. And I told you, you need to remember this, that whenever kinetic friction is acting between two bodies, static friction is acting between two bodies. This is the trick that we use to solve problems. So whenever you have static friction, you need to remember net work done by static friction. Net work by static friction. That means by both its components, both the action and reaction pairs, is always zero. So that's the trick that you use here. Okay? That is the trick that you're using here. You cannot find the force, find the work done on the man easily. Why? Because of the muscle force is also doing work. So if you try to apply work energy theorem on the man, the problem is that you do not know how much work the muscle forces did. However, you can apply the work energy theorem easily for the plant. Why? there is no other force acting on the plank. The only thing that is doing work on the plank is the force of static friction. So using momentum conservation, you will realize that the plank would be moving with V by 4. If it is moving with V by 4, then using work energy theorem, I can calculate that the work done on the friction is 1 over plus 1 over 8 mv square. And since the force of static friction did plus 1 over 8 mv square amount of work, on the man it will do a minus half 1 over 8 mv square. Why? Because we are using this logic. The net work by static friction is always 0. Again, I'm not going to prove that here for class 11 students. Maybe I'll prove it, but I'm not proving that right now because that takes a lot. That does take some time. So using that, I get the work done by friction on man is minus 1 over 8 mv square. And now I can use the work energy theorem to find the work that his muscles are doing. Alright. The net work on the man is half mv square, but both by the muscles and by the friction. So since friction did negative work and this guy net got half mv square, so the work done by muscles must be half mv square plus 1 over 8 mv square. You could have said that in a different manner also. What? That consider initially the entire system, both man and mass, man and plank did not have any kinetic energy, right? They don't have any external force acting on it. So later, when both of them have started moving, who is providing the total energy? The static friction will do no net work because I am already considering the two as a part of my system. So who is providing this kinetic energy to my entire system? It's the muscle work of the man. So you could have also said it in other words, that the muscle work of the man is providing kinetic energy to both the man and the plank. So it will be the sum of half mv square plus this. Alright, that is another way of saying this. I hope you followed that, Pawan. This is a tricky thing, but think about it. It will probably make sense. It's very easy to calculate, but just conceptually it is slightly tricky. Once the concept becomes clear, it's nothing. The maths is very easy. The calculation, there is hardly any calculation. Just conceptually, this is a tricky situation. So I hope the concept is clear. Alright, because there is where I would like to end the day's discussion. Abhi Chamka Pawan, is this okay now? Did you get the concept? I hope you did, because that is what that is it. That is the time that I have for today. So before I sign off, let me also tell you, let me remind you how to get the Unacademy subscription. Get the app, install the app, go to the plus section, select IIT JEE as your target, and click on Get Subscription. That's all right, Pawan. That's all right. I'm sure you guys can share this, and maybe more and more people will come to know, and they will also realize this. All right, more and more can benefit. So that is why you guys need to share it. We are already teaching this, but probably a lot of guys don't even know about this. So share it with your friends. Tell your friends about this. So let's see. Let's hope more people coming here. All right. Also, you realize you will get your Unacademy subscriptions at a very reasonable price, and along with that, you can use my code, which is RDLive, to get an additional 10% off. All right. So don't forget to get your subscriptions using RDLive. And if you like today's video, then press the like button and share it with your friends. Let more and more people know about the amazing content, as Pawan said. All right. Also, don't forget to press the bell icon. All right. The notes of all the slides which are used in this video will be available for download as PDFs by tomorrow. So tomorrow you can come back to and check out the description box. All right. So do not forget to join us through the Telegram app using the link shown there. And one more time, let me remind you, my code is RDLive, and you can get your subscriptions using this code and get an additional 10% off. And of course, amazing content like this and more will be taught to you in your plus courses. All right. So I'll see you guys tomorrow then. Till then, take care. Bye-bye.